Hello YouTube. In this video I'm going to kind of do a brief overview of what we mean when we hear somebody talk about conic sections in math, okay? And just basically kind of what they are, why we might like to explore them and basically, why they might be relevant in terms of like maybe a calculus perspective. So let's go ahead and start with conic section. The base word here of conic being cone. So basically, we say conic up here. We say base word is cone. But you can see I've written here. I know people like to pause the video sometimes and write down some notes maybe. But we say a conic section basically is this. It deals with a double napped cone is what we call it. You can see I have these diagrams down here. But a double napped cone basically means these two cones arranged such that their two vertices are arranged kind of upright on top of one another. But basically, what I can tell you is the ancient Greeks, of course, explored different shapes. Some of these that you see here, like a circle, ellipse, parabola, hyperbola, of course, like points, lines, and intersecting lines. But they explored these, and they didn't necessarily have the use of the xy coordinate plane as we have it today. And the nice thing about the xy coordinate plane is that the xy coordinate plane, we can define things algebraically and solve for unknown distances and like basically measure things. So whereas we often today say like draw an ellipse in the xy coordinate plane here, we could make it like kind of a flattened circle. This would be our ellipse here. We could define this in terms of some xy equation and use that equation to kind of measure things about it, which is really convenient when you're like, trying to find the area, say inside of here in calculus. You want an equation for that curve so you can maybe like integrate or find the slope of a line tangent to this ellipse at a given point. We use differentiation. So basically, the whole intent of studying conic sections is to take the ancient Greek idea of what a conic section is and make it into kind of an XY perspective so that we can measure things, kind of more efficiently and basically more purely. So what is a conic section really? Basically, the Greeks said, if you could imagine these two cones arranged upside down on top of one another, like like you see here, these double napped cones. Imagine a two-dimensional flat plane, so like a linear plane, intersecting these cones at different various kind of orientations. So if we were to necessarily see the circle here, if we were to pass this plane through, left, right, you can see it kind of passes through flat. You see you get this circle of points here. This like this cross section where it hits the cone. Or an ellipse would be kind of the same thing as a circle, but if you could tilt the plane so that it kind of hits at this flattened circle kind of pattern here, like I kind of drew on the right. Or the parabola, which is basically like we see here on the ellipse, but if we were to tilt the plane enough so that it would pop off the edge of the cone, you'd have this parabola intersection cross-section thing. And then a hyperbola, just, people like to say it's like a parabola. I like to tell you, no, it's not. And it's not. But basically, you see this kind of like double, almost parabola-looking thing. But we can basically say this intersection, this cross-section where these two things intersect or coincide, we say it forms a locus of points. So one very important thing to get from this video is this. We say a locus of points is just a collection, okay, of points. But basically the collection of points that satisfy like some given condition. Satisfy given condition. Okay. And so we're going to develop this a little bit more formally here in a second. But we say this collection of points that satisfy a given condition or this locus of points are the ones that we're concerned with in this cross section here. Okay. One very important thing to kind of point out is this. We have these things called degenerate conics. So these are the ones listed down here. You can kind of see degenerate conics are degenerate because this and only this, but basically they go through like the vertices of the cones. So any way you could orient this plane, you'd see like you'd get a point if you were to pass the plane through, kind of like a circle, but at their vertices there, it's like a singularity, it's a small point. Whereas a line would kind of intersect the side of each of the cones, and then two intersecting lines would be kind of an upright plane. So basically, that being said, we take into consideration this here, a couple other things. We say the general form of an equation. So this is really important here. But we say the general form of an equation. When you're studying conic sections, remember, the intent of studying a conic section in the first place is to take this classical Greek idea of what the shape is, this pure shape, this collection of points that satisfy a given condition. We call that collection of points a locus. But take that conic section and define it more in terms of x and y so that we can measure things using calculus. So one important thing to mention here is this. We say the general form of an equation in conic sections looks like this. So you're going to notice a few peculiarities here, but we say capital letters for all of our coefficients, we see we have one constant term, that's our f at the end here, and it's equal to 0. So the important thing to remember about general form is that everything's on the left here that has a variable or is a constant or has substance, and 0's on the right. And the other characteristics are these. We say we have an x squared term and a y squared term, and typically we put these in this order. We say x squared, and then this odd little xy term in the middle, x first, y first, and then y squared. Then we have plus a dx plus ey plus f. And it's very important that we actually are able to write things in general form. And so you might practice that given different equations. But to kind of show you what I mean about conic sections being defined in terms of x, y instead of a classical Greek idea, let's take a look at this. But, you can pause the video and read this if you need to. But I say a locus of points is a set of points, of course. You hear me say this over and over again, that satisfy a given condition. Recall it as a circle. Okay, in the xy coordinate plane, which is probably how you're used to sort of defining this thing here, but we say this circle, has a focus, okay, and the focus is kind of a really important point that you see I can highlight it here, the focus. It's kind of how we gather this locus of points here, but we say all of the points on the outside of this circle are in a locus of points, and they are in a locus of points, or a collection of points, that satisfy the condition that no matter how far or what point I choose in this locus of points, let's put it that way, what x, y I choose on the outside, it'll be the same distance to the focus. And so we could define a circle like that. And then, that's easy to show, but we could also say, in terms of xy coordinate plane, we say a few things are true about this. We say that the center of the circle is at hk, okay, and we say the radius here is a radius r. And so, you're probably used to seeing this equation that I can highlight here, but this is the equation of a circle. With center at hk and radius r, but basically in terms of x and y, as opposed to kind of saying, oh, this is a cross section of a plane, which is the xy coordinate plane, and some cone. If you can imagine, here's our cone, and we say, we're passing our plane through at a flat angle. You get this circular point right here. We say, hey, this is maybe our xy coordinate plane here. It's kind of very poorly drawn, but you can see what we mean by this. So, future videos we're going to be talking about circles, ellipses, parabolas, hyperbolas, you name it, but we're going to define these all in terms of very general equations we need to get used to. So cheers.